Mr. Poley sick today. Me, Frankenstein, here to teach you direct variation. P.S. Happy Friday. Tomorrow Halloween. Full moon. Spooky. Page 77. Now, we do notes on direct variation. Page 77, 78. So, direct variation. That is the topic for today. Moving on to Unit 3, which starts our unit on linear functions. So last unit was all about functions in general. Now we're moving into linear functions. And then we will eventually get to quadratics and exponential and logarithmic. It's a whole list of fun functions to explore. And I know linear functions aren't the most scary. That's what we're doing today. It just happens to be Halloween, and we're learning about direct variation, starting our unit on linear functions. So direct variation may or may not be a term or topic that you are familiar with already, and that's okay. Okay, a direct variation means that two variables they are directly related to each other, which means they are proportional. So I hope that is a word that you've heard before. Proportional means we can use proportions throughout this topic. Hopefully, when you hear the word proportion, you think of fractions. I know fractions may be a little scary, so maybe it's a good thing we're doing these today. Okay, so let's see here. We say that two variables, namely y and x and y, they are directly related or proportional to each other if this following relationship holds. So two variables, x and y, have a direct or proportional relationship if for every ordered pair xy, we have y over x equals k. Or we can do a little rearranging there, multiply both sides by x to get y equals k times x. Let me zoom in here and see if this... Oh. Okay, and what that means when we write it as y equals k times x, y will always be a constant multiple of x. The value of k is known as the constant of variation. Okay, and of course, y is your dependent variable, x is your independent, so y still depends on x. And in this kind of relationship, if x goes up, y is going to go up. If x goes down, same thing for y. Okay, so that is the idea here of a direct relationship. Actually, I guess I forget that last part I said. Frankenstein made a mistake. Okay, it's just as x changes, y will also change. Okay, it doesn't necessarily have to be one goes up, the other goes up. So one can go down while the other goes up, or vice versa. Okay, but it's as x changes, y will also change. They are directly related. Okay, and you can see my screen's being a little funky again. It's just how it goes, I guess, on All Hallows Eve. All right, so we're going to look at a couple examples here, just straightforward with numbers. Then we get into some wordy problems. All right, in each of the following, x and y are directly related, meaning this relationship up top holds true for each of these situations. So we want to solve for the missing value. All right, so based on this relationship here, we know that when we take y and divide it by x, I'll try to stay off the screen so you guys can see. When we take y and divide it by x, that is going to be equal to k, that constant of variation. Okay, that's going to have a set value in this situation here. Okay, and since the x and y that are given here and the y we need to find are part of, you can think of them as part of that same set, that's going to be equal to another y divided by x. So I'm going to take the first y and x that I have and plug those in here. So I have 15 over 5. Okay? And I know that's equal to k. Maybe you guys can already figure out what k is. But I'm going to pretend k is not there for a minute. Okay? I'm going to take k away since these three things, since y over x is equal to k, which is equal to y over x, another y over x, I can take k out and just use the two fractions, the two proportions on the ends. So I would take y, which I don't know, I need to find that y, and that's divided by 9. So I have 15 over 5, I took the first y and x they gave me, and I set that equal to y over 9, because I don't know that second y, but I know what x is there. So now when we have a proportion set up like this, we have a proportional relationship between two sets of values. Do you guys remember how we solve something like this? It's a fancy little term, a fancy little trick. I think some of you are thinking cross multiply. That's right. Okay, so we take this 15 on top, multiply that by the 9. We take this 5 on the bottom and multiply that by y. Okay, hopefully you guys wrote a little bit smaller than I did. Frankenstein's a big guy, so you can understand why he would write big as well. Okay, 15 times 9 will give us 135, and that's equal to 5y. Okay, we can solve that now. We got a one-step equation, which we are professionals with. This 5 is being multiplied by y, so I divide by 5. And divide by 5 there. And that comes out to be, I know this is a little messy, hope you can follow what I'm doing here, y equals 27. And we were able to find that value because we know that y and x are directly related to each other there. They have a proportional relationship. Okay? And here, the k value, just as a side note, that constant of variation, the thing that holds true for any xy in this relationship here, that k value would be 3. So you have 15 over 5 is 3. 15 divided by 5 is 3. Or, now that we know this is 27, 27 divided by 9 is also 3. Just trying to fool around with the lighting here. Oh. Okay, moving on to letter B. Same idea holds true, right? We take 1 y and x, so we have negative 6 over 4. And that's going to be equal to, I'm going to skip the part where I write in k because I know that 1 y over x has to equal the other y over x. So negative 6 over 4 equals y over negative 10. All right, and again, a little cross multiply action. Take that numerator on the left, multiply by the denominator on the right, and take the denominator on the left, multiply by the numerator on the right. Just like that, you get a nice little butterfly picture. Maybe you're a little more artsy than me and can actually turn that into a butterfly. Although that's not very spooky, so I don't know why you would. So negative 6 times negative 10 is 60 equals 4y. And then solving for y, we get y equals 15. And again, we're able to do that because we know those variables are directly related to each other. So this proportional relationship holds true. Okay, and the last one here, boom, boom, boom. 12 over 16, y over x equals y over 24. Okay, I will leave that one for you guys. Moving on to exercise 2. Now we're actually working with some real stuff here, right? Distance and time. Someone's going on a road trip. I like to take road trips. I think about this stuff all the time. If I'm driving so many miles in this much time, how many miles can I go in this much time? It's exactly what this question is all about. The distance a person can travel varies directly. So again, there's that direct relationship. And whatever thing varies directly with the other thing, so the distance a person can travel, any guesses if that's our dependent or independent? Is that our y or our x? Well, that's the thing that varies directly with the other thing. The distance equals y. That is our dependent variable, right? Because that distance depends on the time. Remember, time waits for no one, but distance depends on time. So the distance a person can travel varies directly, of course that's important there, with the time they've been traveling, if going at a constant speed. Constant speed, guys, that is a key word for this unit, for this lesson. And maybe the unit. Ooh, who knows? Okay, constant speed, that's a key. That's a key, or just constant in general. Okay, because that means we have a constant of variation, that k value. All right, so our time is x. So if Phoenix is a person here, Phoenix traveled 78 miles in 1.5 hours. Okay, so I'm doing, to set up this relationship here, I have distance over time. So my first values they give me here, 78 miles over 1.5 hours. And again, it specifies he was going at a constant speed. So how far will he travel in 2 hours at this same speed? So that means we can set up this proportion here, this direct relationship. Now I don't know how many miles he's going. That's what I'm wondering. Okay, so I have a unknown y value there. Now on the bottom here, I have 2 hours. Okay, so again, we do a little cross multiplication action. Oh, don't want to move that. So we get 156 equals 1.5y. Again, something we've solved a bunch of times before. If we have a number next to a variable, divide by that number, and we get y equals 104 miles. That means Phoenix could travel 104 miles in 2 hours if he kept that same speed. All right. There we go. Not too bad, right? Just yell at Frankenstein if you have any questions. All right, Jenna works a job. Jenna, you out there? You're working a job. Her pay varies directly. So again, her pay varies directly with the number of hours she has worked. Okay, so again, we know this is a direct relationship. These things are proportional to each other. So now it's her pay that is the dependent or y variable. And hours worked is the independent x variable. Okay, so her pay is directly related to the hours worked, and her pay depends on how much she works. All right. In 1 week, she worked 35 hours and made $274.75. So I'm going to set this up again. I have my pay over my hours. Or sorry, Jenna's pay over Jenna's hours. Jenna, you're working a lot, huh? 35 hours. Wow, how do you keep up with that and schoolwork? It's motivation right there. What a go-getter. All right, so we have 274.75 over 35. This is dollars. This is hours. So we're kind of setting up a rate here, right? Dollars per hour. Up here we had miles per hour. Okay, we're really working with rates. How many hours would she need to work in order to earn $337.55? So now we have her desired pay here, $337.55, a very specific amount, I might add. And we're wondering how many hours would it take her to earn that much money? Okay, if she's making the same amount per hour as she was here. So again, cross multiply these. Okay, we get 274.75x equals 11,814.25. All right. And again, hopefully you guys can see that there. Last thing would be to divide by this 274.75. Divide by that there. Figure out how many hours exactly she would need to work. Okay, and that comes out to be 43 hours. All right, I mean, it sounded like 35 hours was a lot before, but 43, she's going to be making some overtime, guys. Way to go. All right, so just a couple examples there of direct variation in that direct relationship. All right. On to the back, page 78. Who's still with Frankenstein? Ooh. Now we'll examine the graph of a direct relationship and see why it is indeed the simplest of all linear functions. So we have two variables again, x and y. What do you know? They vary directly. When x equals 6, then y equals 4. And that point is shown plotted below. So I'm just going to label that. That's 6, 4. So we're asked to find the y values for each of the following x values, plot each point, and connect. Okay? So my x is 6, y is 4. So again, when I set up y over x, I have 4 over 6 equals y over 3. That's for x equals 3. We're trying to find that y value. Set up the similar thing over here. Again, using the same first point that they gave us, 4 over 6, I know that's going to be equal to y over negative 6. Okay, we're trying to find the missing y value so we could plot a couple more points and see what we're really working with here. All right, so when I solve this over here, a quick cross multiply, I get y equals 2. So when y is 2, x was 3. So there's my point, 3, 2. X is 3, y is 2. Same thing here when I cross multiply and solve for y. I get y equals negative 4. So here, maybe I'll write those points real quick. All right, I have the point 3, 2, which I already plotted, and now negative 6, negative 4 is way down here. It says plot each point and connect. So guys, use your straight edge, not like me, and connect those points. Shouldn't have gone past. Okay. So what is the constant of variation in this problem? And by the way, did you guys notice what happened on this graph? We went right through the origin. Right through the origin. That's true for every direct relationship. Every time variables vary directly with each other, that means it's going to go through the origin because there is no starting value, right? It's just x and y. There's no other factors or constants in play here. So what is the constant of variation in this problem? Well, remember that's asking what is k? And what is k equal to from our front box, the notes on the front? That's right. K is equal to y divided by x. Okay, y divided by x. And, well, we can use our original point here. X was 6, y was 4. So I have 4 over 6, which comes out to 2 over 3. So that is my constant of variation, 2 over 3. Now think closely here, or carefully, closely and carefully, why not? What does this constant of variation represent on this line? 2 over 3, 2/3. What could that possibly give us for this line here? Do you guys see it? Okay. That is the slope of this line. Right? 2 over 3, that's our rise over run. Look, from this point to get to here, we go up 2 over 3. From the origin, up 2 over 3. That 2 over 3 is our slope. That will always be true for a constant of variation when the variables are directly related. That constant of variation is the slope of the line. And the line, when we're working with direct variation, that line goes through the origin, which that's why this is the simplest of all linear functions. So write the equation of the line you plotted. So remember, y equals mx plus b. Everybody loves that formula, that equation. Well, our b value is 0, because that's the y-intercept. So technically, I don't want to say there is no b, but b equals 0, so we will not be writing a b in our equation. And remember, when you write the equation of a line, you keep y and x there, and just substitute in the slope and y-intercept. So our equation for this line is y equals 2/3 x. M is our slope, 2/3 is our slope, which is also our constant of variation. So y equals 2/3 x. Each of these points that we have here, our original 6, 4, the 2 we plotted, 3, 2, and -6, -4, satisfy this equation. All right? And a nice little note there says direct relationships often exist between two variables whose values are 0 simultaneously. Okay? And that's what's happening at the origin here. X and Y are both 0. Their values are 0 at the same time. All right, guys, let's wrap this up here. We're almost done. Exercise 5, the miles driven by a car, D, varies directly with the number of gallons, G. Okay, so D, miles driven, varies directly with number of gallons, G. So D varies directly. That means D is technically our Y variable and G is technically our X variable. But we will be using D and G because that's what they give us. Abigail is able to drive D equals 336 miles on G equals 8 gallons of gasoline. in her hybrid vehicle. She's very environmentally friendly, environmentally conscious. So let's calculate the constant of variation for the relationship d over g. Okay, and remember, k is our constant of variation, which is equal to y over x, which in this case is equal to d over g. So let's use the values, the amounts they gave us. 336 miles over 8 gallons. Okay, a little quick computation, quick division there. Gives us a constant of variation of 42. And it does say to include proper units. So what are the units here? What two things are we dividing? We have miles per gallon, also known as MPG. If you guys are into cars, 42 miles per gallon is MPG. That's pretty good gas mileage. And it's a hybrid, so it makes sense. Okay, 42 miles per gallon is the constant of variation. Let's give a linear equation that represents this relationship between D and G. Okay, remember above what that constant of variation represented. That represents the slope. Okay, that's a constant rate here. And it has to be constant because we're talking about linear relationships. So again, we want to try to set up y equals mx plus b. But in all direct relationships, that b value is 0. So I'm going to get rid of that b. Now I know that y is my d, m is my constant of variation, which is 42, and g, oops, as I say g, I write x. Okay, g is our x. So this is our equation, our linear equation that represents this situation here. D equals 42g. Okay, that means for every gallon, for every 1 gallon, she's able to go 42 miles. All right, that's exactly what this is showing. And her distance traveled, the number of miles she can go, depends directly on how many gallons she has. All right, so 2 last questions here. How far can Abigail drive on G equals 6 gallons of gas? Well, since we have this equation already made up for ourselves, let's go ahead and use it. So D equals 42G. And they give me how many gallons Abigail has, so D equals 42 times 6. And that comes out to be 252 miles. And we were able to find that, again, because that direct relationship holds true. All right, last one. Again, using that same equation. How many gallons of gas will Abigail need in order to drive 483 miles? Okay, now we're given the number of miles she wants to drive. So we substitute in for D. 483 equals 42G. Now we got to solve for G. How many gallons does she need to drive that far? Okay, quick division here. Divide by 42. Gives us, what was it? 11.5 gallons. And that's about it for Abigail. Hopefully she'll reach her destination just like we have done. My bolts are coming loose. That means my head's about to fall off. Hopefully not. So, thank you guys. Paying attention, staying with me. Happy Halloween.